Hello friends, welcome back to my channel. This is second lecture in my lecture series on distillation. In my first lecture, I have discussed fundamentals of distillation. I hope you have seen that lecture. If not, you please see it to understand the basics of distillation. So in this part, in second part, I am going to talk about material balance for distillation. So this is distillation part 2 and we are going to discuss material balance for distillation in it. So let us learn how to write material balance for distillation. Here we are going to consider distillation of a binary liquid solution. What is a binary liquid solution? A liquid solution that is having only two components in it. So we are going to consider distillation of such a binary liquid solution. First, let us learn how to represent the operation of distillation using a block diagram. So in this block diagram, we are going to represent distillation by this rectangle. This rectangle represents the distillation operation. Now you just have to show all the streams that are associated with the distillation operation. Of course, the first stream that is associated with it is the feed stream. So that is the feed solution. And in our discussion, this feed solution is going to be described by these two parameters, F and XF. I'll tell you what are these parameters shortly. Then there are two streams that come out of the distillation operation. So if you remember the basics, if you have seen my previous lecture, you will come to know that there are two streams that will come out of the operation. One stream that is removed from the bottom, that stream we call that as residue or the bottom product. And here we are going to describe this residue by these two parameters W and XW. We will shortly understand what are this. Then the other stream that comes out of the operation is distillate, or the top product, or the overhead product. And here we are going to describe this by using these two parameters D and XT. Okay, so by using this simple block diagram, we have represented the distillation operation. So input is the feed solution and there are two output streams. One is residue and the other one is distillate. Okay, now the feed solution, let us know more about feed solution. So as I said earlier, this feed solution is a binary mixture of A and B, a binary liquid solution of A and B. There are only two components, one is A and the other one is B. Out of this two components, A is the low boiling component, or in other words, A is the more volatile component. A is the low boiling component. Now what material balances are to be discussed over here? First, we are going to discuss how we can write material balance for total modes, or how we can write balance for total modes. So this is total material balance, and then we will learn how to write balance for modes of A, that is the more volatile component. So this will be the component material balance. Okay. So in this discussion, our objective is to discuss total material balance, which will take balance for total modes, and then material balance for the component, or the component material balance. Which component? More volatile component. Okay. So these two balances we are going to discuss over here. And all these material balances, total material balance and material component material balance, we are going to discuss under steady state conditions. We are going to discuss these material balances under steady state conditions. What are steady state conditions? Steady state conditions imply nothing changes with respect to time. There is no change with respect to time. So Material balances we will discuss under steady state conditions. Okay. Now let us talk about the notations that are used in this discussion. So over here you can see there are 6 different notations: F, XF, WXW, DXD. What are these notations? Let us first understand. F, here F is representing moles or molar flow rate of the feed, moles of the feed or molar flow rate of the feed. How to describe molar flow rate, or how is molar flow rate defined? It is defined as, for example, it could be kilomole per second, kilomole per hour, or moles per second, mole per hour. So F represent moles or molar flow rate of the feed. XF, it represents mole fraction of A in the feed. That is mole fraction of more volatile component in the feed. XF represent mole fraction of more volatile component in the feed, and in this case the more volatile component is A. Then D is representing moles or molar flow rate of the distillate. XD is representing mole fraction of A in the distillate, or mole fraction of more volatile component in the distillate. W, it is representing moles or molar flow rate of the residue, and XW, it is representing mole fraction of A in the residue. Okay, so all these 6 notifications that we are going to use in this discussion, they are described over here. Okay, now let us move on. Let us first write total material balance. By total material balance, we mean we are going to write balance for total moles. So how will it be written? It will be written like this: Tm in minus Tm out is equal to Tm accumulated. What is Tm in this case? Tm is total moles. Okay, so total material balance, that is balance for total moles, is written in this way: total moles into the operation minus total moles out of the operation, that is equal to total moles accumulated within the operation. Tm is total moles. But since we have decided to discuss material balance under steady state conditions, so at steady state conditions or under steady state conditions, accumulation is zero. There is no accumulation. So accumulation term will be a differential term, differential with respect to time. And once we say that steady state conditions are prevailing, then all derivatives with respect to time will be equal to zero. That is why accumulation becomes zero under steady state conditions. So if you use this in this equation, this equation will get modified to this form: total moles in minus total moles out is equal to zero. That is, if you rearrange this equation, you will have total moles in, that is equal to total moles out. Okay, next we will write it in mathematical form. So now we know how the total material balance is written under steady state conditions. It is simply total moles in is equal to total moles. Okay. So we have already got this equation. Now let us write total moles that go into the operation, and then on the other side, or other side, we will write total moles that comes out of the operation. Total moles that go into the operation, they are going along with the feed. Therefore, on the left hand side of this equation, you will be having total moles of feed. Okay. On the right hand side, we have to write total moles that are going out of the operation. So total moles will be going out along with the distillate stream and along with the residue stream. So that's why on the right hand side of this equation, you have total moles of distillate plus total moles of residue. So total moles under steady state conditions, feed that enters the operation, it will either come out as distillate or it will come out as a residue. So this is the balance written under steady state conditions. So mathematically, since we have already defined various notations, to total moles of feed, they are represented by F. So it will, the mathematical equation will be simply F is equal to D plus W, and let us call this as equation 1. Let us call this as equation 1. Now what does equation 1 give? Equation 1 give the total material balance, balance for total moles. Okay. Okay. Then after that, let us discuss material balance for component A. So this is component material balance, where we are going to write material balance for the more volatile component. And in this case, A is the more volatile component. So how is this written? Moles of A in, total moles of A in, or simply you say moles of A in minus moles of A out, that is equal to moles of A accumulated. So that is Ma in minus Ma out is equal to Ma accumulated. Ma represents moles of A. So you have moles of A in minus moles of A out, that is equal to moles of A accumulated. Again, at steady state, accumulation is 0. Accumulation is 0. That is, moles of A getting accumulated within the operation, it will be 0 under steady state conditions. Okay. So if that is used, the equation now will be written as moles of A in minus moles of A out, that is equal to 0. Or if you rearrange the equation, on the left hand side you have moles of A in, and on the right hand side you have moles of A out. Okay. Now once we know how to write material balance for component A under steady state condition, now let us write it in terms of a mathematical equation. Okay. So moles of A in my is equal to moles of A out. This is what we got under steady state condition. So A, it will be going into the operation along with the feed stream, and it will be coming out along with the distillate, as well as it will come out along with the residue. It will go in the feed and it will come out in distillate and residue. So the balance is written like this: moles of A in the feed, that is equal to moles of A in distillate plus moles of A in the residue. Now let us write this in the form of a mathematical equation. So moles of A into the feed, or moles of A in the feed, how to express that in mathematically? So it will be expressed like this: F into XF. F F is total moles of the feed, and if you multiply with mole fraction of the more volatile component, that is mole fraction of A, then you will get moles of A. Okay. So moles of A in the feed, they are given as F into XF. Similarly, moles of A in the distillate, they will be given as D into XD, and moles of A in the residue, they will be given as W into XW. Okay. So you have this equation. Material balance written for component A gives us this equation: F into XF, that is equal to D into XD plus W into XW. And now let us call this as equation 2. So equation 2, it gives the material balance written for component A. Okay. You can also write material balance for component B. Okay. So it will be moles of B in is equal to moles of B out, that is moles of B in feed is equal to moles of B in distillate plus moles of B in residue. Okay. Since there are only two components, if XF is mole fraction of A, mole fraction of B will be 1 minus XF. And on this side, if XD is mole fraction of A, 1 minus XD will be mole fraction of B. Similarly, over here it will be 1 minus XW. 1 minus XW will give mole fraction of B. Okay. So balance for B will be written as F into 1 minus XF, that is equal to D into 1 minus XD plus W into 1 minus XW. ठीक है. Since there are only two components, it is sufficient for us to write material balance for one component. That balance for other component, there is no need for writing balance for other component because there are only two components. Okay, so equation 2 gives material balance for component A, the more volatile component. Okay, now let us move ahead. So basically, when you have a binary liquid solution in which one component is more volatile, then you just have two equations to describe the material balance. One is total material balance, that is balance for total moles, and other one is material balance for the more volatile component, that is balance for moles of A, balance for moles of more volatile component. Okay, so we have those two equations. First equation is F is equal to D plus W, and the second equation is F into XF, that is equal to D into XT plus W into XW. Okay, now we will learn how to use this two equations, and for that we are going to discuss one numerical. Okay, so first I'll show you the statement, numerical statement. So I'll just read it. A feed mixture is comprising 42 mole percent heptane and 58 mole percent ethyl benzene. It is to be distilled to yield an overhead product containing 97 mole percent heptane and a residue containing 99 mole percent of ethyl benzene. And we have to find out moles of distillate and the residue. Okay. So as usual, my suggestion is if you have to solve any numerical, you first read the given statement carefully and try to collect the given information. First try to collect the given information, and then you organize your calculation so that you get the desired result. Here we have to get moles of distillate and residue. Okay, so first of all, let us write down the given things. What is given to us? The feed solution is given, and the feed solution is containing two components. So it is a simple binary liquid solution. There are two components. Which are these two components? One is heptane and the other one is ethyl benzene. Distillate contains majority of heptane. So in the statement they have said that it is to be distilled to yield an overhead product containing 97 mole percent of heptane. That means 97 mole percent of heptane is in distillate. The remaining 3% is the other component, which is that component ethyl benzene. Okay. So you can identify the more volatile component. Major component in distillate is the more volatile component. So in this case, distillate is containing majority of heptane. To be exact, it is containing 97 mole percent of heptane. So we can conclude that heptane is the more volatile component. Okay. So since distillate is containing majority of heptane, hence it is the more volatile component. The feed rate is not given, but its composition is given. Again, this is important to note. Here, feed flow rate, molar flow rate of feed is not given, or moles of feed, they are not given. Okay. But what is known to us, its composition is known. We know that feed contains 42 mole percent heptane and 58 mole percent ethyl benzene. Okay. So in such cases, what you have to do, the composition, whatever is given, the composition is given in mole percent. Okay. So in this case, what you have to do, you have to start with a suitable basis. You have to start with a suitable basis for solving this numerical. When this is to be done, when feed rate is not known to us, quantity of feed is not known to us, but composition is known. Composition could be either mole percent or weight percent. In this case, it is mole percent. Even if it is given in weight percent, you can convert to mole percent. So in coming lectures, I'll tell you, we will be discussing how you can convert weight percent into mole percent. Okay, so the point is, whenever feed rate is not given and composition of the feed is known to us, you start with a suitable basis. A suitable basis is used for solving the numerical. And what basis we are going to choose? This is the best basis, 100 kilomole per hour, or you can call it as 100 mole per hour, 100 kilomole per second. Okay, a suitable basis has to be assumed in the beginning. This will come into picture when feed rate is not given to us and only composition is given. Okay? Further, XF is given, composition of feed. Since we have already identified that heptane is the more volatile component, and the feed is containing 42 mole percent of heptane in it, that means XF is known to us. XF will be 0.42. Why 0.42? Because feed is containing 42 mole percent heptane. So here you can convert mole percent to mole fractions by simply dividing with 100. So I have simply divided with 100 and I have got this figure. XF is equal to 0.42. Then other thing that is given is XD. The distillate is going to contain 97 mole percent of heptane. So accordingly, XD will be 0.97. 97 mole percent simply divided with 100 and we get this. XD is equal to 0.97. Okay. The residue is containing 99 mole percent of ethyl benzene. Since ethyl benzene is the less volatile component, it will be the major component in the residue. And here they are saying that the residue is containing 99 mole percent of ethyl benzene. So remaining 1 mole percent will be heptane, the more volatile component. Okay. So since residue is containing 99 mole percent of ethyl benzene, it contains 100 minus 99, that is 1 mole percent of heptane, and this is of our interest. Okay. So therefore XW will be 0.01, 1 mole percent, and this mole percent will be converted to fraction by dividing it with 100. So XW will be 0.01. Okay. So with all this given information, we are supposed to get D and W. D and W are to be calculated. Okay. Now let us start the solution. Okay. The total, we have to use two equations. Which are these two equations? One is the total material balance, balance for total modes. Other one is component material balance, balance for moles of mole volatile component. Okay. So let us first write down the total material balance. So it is F is equal to D plus W. We have assumed basis of 100 F to be 100, so it will be 100 is equal to D plus W, and let us call this as equation 1. So we have got equation 1. There are two unknowns in this equation, and if you have to get this their values, we need another equation in terms of these two quantities, D and W. And what is the source of that equation? Source is more volatile component material balance, or material balance for more volatile component. We know how it is written. It is written as F into XF is equal to D into XD plus W into XW. Now, whichever quantities are known to us, let us use those quantities in this equation. So F we have assumed it to be 100. So on the left hand side, you will be having 100 into 0.42, because XF is 0.42. That is equal to D is not known to us, but XD is known. So it will be D into 0.97 plus W is not known to us. So it will be W into 0.01, because XW is known to us. Okay, so if you simplify it, 100 into 0.42 is 42. So it will be 42 is equal to 0.97D plus zero point zero 0.01 W. Let us call this as equation 2. Okay, so now you have equation 1, which is in terms of D and W, and you have equation 2, which is again in terms of d and w. Okay, so now you have two equations, there are two unknowns. Only job left is you have to solve these two equations simultaneously. Now let us solve these two equations. So how are we going to solve this? From equation 1 I will get equation for w. So from equation 1 w will be 100 minus d, and you can easily guess what I will do with this. I will use this in equation 2. So wherever there is w in equation 2, I will replace it with 100 minus t. So if I do it, if I use it in equation 2, I have 42 is equal to 0.97d plus 0.01. Now in place of w, I have written 100 minus t. Okay. Further we have to simplify it. So it will be 42 is equal to 0.97d plus 1 minus 0.01 d. Okay, 0.01 into 100 is 1 and 0.01 into d is 0.01 d. Okay, simplify it further. So 42, when this 1 comes on this side, so it will be 42 minus 1, that is 41, and 0.97d minus 0.01d is 0.96d. So that will give us d as 41 divided by 0.96, which comes out to be 42.71 kilomole per hour. Okay, so in these steps we get d. Now what is left? We have to get value for w. So let us do it. Okay, since previously just now we got d as 42.71 kilomole per hour. Okay, w is 100 minus d. You just have to use the value of d. So w will be 100 minus 42.71. That is w is equal to the result is 57.29 kilomole per hour. Okay, so in these steps we get w. We have already got d. Okay, so at the end we have to report these two values d and w. So d comes out to be 42.71 kilomole per hour and w comes out to be 57.29 kilomole per hour. Okay, so that is the end of it. So at the end, for this numerical we have to report these two values. Okay, so in this way we can use material balance equations for solving numericals like this. Okay, in coming lectures I'll be discussing more numericals based on material balance. Okay, so in today's lecture, in part 2 of my lecture series, I have talked about material balance for distillation. So I have discussed material balance for a simple binary liquid solution as the feed. We have learned how to represent distillation by using a block diagram, and then how to write material balance for the distillation operation. Sorry. Okay. So with this I end my discussion for this part. You please subscribe to my channel and hit the bell icon so that be you'll be notified as soon as I upload any video on my YouTube channel. In coming days I'll be uploading various videos on distillation. So please subscribe to my channel and hit the bell icon. Okay. Thank you for being with me for this lecture. Thank you.